Hey guys, Mr. Fawcett here, and today we are back with another lesson in our AP Calc AB timeline. This time it is for infinite limits. So we've touched on this topic briefly in previous lessons. I've kind of always said we're going to get to it eventually, and it deals with vertical asymptotes. Now, when we've had a vertical asymptote in a function, we've always said the limit does not exist as x approaches that x value. But I've always said eventually we'll start talking about infinite limits, and instead of saying does not exist, we can be more specific and talk about whether the function is approaching positive infinity or whether it is approaching negative infinity. And again, that just gives the reader a better idea of what's going on at that x value rather than just saying the limit does not exist. So to start off, we have a function f of x, and we are asked to identify the x values for which f of x has a vertical asymptote. So pause the video, take a minute or two to identify that x value, and not only identify it, but try to explain in your head or either out loud about why there's a vertical asymptote there, and maybe the difference between a vertical asymptote as opposed to a point discontinuity. Okay, so hopefully you've had time to answer this question regarding the vertical asymptote. Short answer is the vertical asymptote appears at x equals 2. But we want to be able to talk about why that's the case. Why isn't there a point discontinuity at x equals 2, which would be just when we have a hole in the graph? Well, it has to do about whether this factor right here is also a factor in the numerator. So if we had a factor of x minus 2 in the numerator, then we would have a point discontinuity or a removable discontinuity or a hole in the graph. All three of those things are the same way of describing, or sorry, they're different ways of describing the same thing. So let me just give you a quick visual. If our function was, I guess we'll call it g of x. It's not to be confusing. So if we had an extra factor in the numerator here, that was also x minus 2, then we would have a point discontinuity at x equals 2. But since the factor x minus 2 is not in the numerator, that's why it's going to become a vertical asymptote instead. Okay, so a little review about vertical asymptotes. Now let's talk about the limits. So previously we went no further and said that if there was a vertical asymptote, then the limit does not exist. This is true if we were talking about real numbers, but there is a category of limits called infinite limits. This is when a function approaches infinity or negative infinity. So for this, actually there's two. There's part A on this page and part B on the next page. For both of these one-sided limits, you can use your calculator. You can write out a table, or you can try to think of it just analytically or algebraically. But I want you to figure out whether this one-sided limit is going to positive infinity or negative infinity. All right, and then I want you to try to be able to justify it. So pause the video and then click play once you've given it a good thought. All right, so hopefully you've given it a go. I am actually going to start with our calculator because I think that's the easiest way initially to try to figure this out, and then we can move into a more analytical approach. All right, hopefully, yeah, you guys should be able to see this. So I've already typed in our function, and I am just going to hit graph. I'm going to zoom in. Looks like we're not zoomed in all the way. Zoom standard. Okay, and we can see that we have a vertical asymptote at x equals 2. Now this limit we were talking about, part A I believe was as x approaches 2 from the negative side. So where's my pen? So So as we approach 2 from the negative side, we can see that our function is approaching negative infinity. And while we're here, we'll just look at what's happening as we approach from the positive side. We can see that our function is approaching positive infinity. We can also check this using a table. Let's actually fix this table so we have a smaller increments. Okay, so I've set the table to go in increments of thousandths, right around x equals 2. And now let's take a look at our table. So we can see as our table is getting closer to 2 from the negative side, these numbers are getting more and more negative. And as we approach 2 from the positive side, they're getting more and more positive. So that's going to show us that they're increasing or decreasing without bound, which means that they're moving towards positive and negative infinity. Okay, let's go back here. So now that we know what these answers are, we might be able to try to work backwards. So this limit is going to be equal to negative infinity. And part B down below would be equal to positive infinity. But let's see if we could figure this out without using our graphing calculator, because maybe we see this question on the non-calculator section of the AP exam. Is there a way for us to look at this and say, okay, as my x values are getting closer and closer to 2, are these numbers getting more negative or are they getting more positive? Well, we can think about it, right? If we have a fraction, so if we have the fraction 7, and then let's pick a number slightly less than 2, so maybe 1.9. Okay, this is going to give us 7 divided by negative 0.1. Well, we don't need a calculator to tell us that this simplified answer is going to be negative, right? It ends up being 70, but we don't need to know the exact answer. We just need to know that it's going to be negative. And if we keep taking numbers that are closer and closer to 2 from the negative side, right? So maybe we do 1.99. So 7 divided by 1.99 minus 2. This will give us 7 divided by negative 0.01, which will give us, this should be negative 770, and then negative 700. You can see as we get closer and closer to 2, those numbers are just become more and more negative. And that's because our numerator is always positive and our denominator is always negative. And you could think about it if we did, I'll just do the work up here for part B, but if I had the limit as x approaches 2 from the positive side, well, if I do 7 divided by 2.1 minus 2, that's going to give me 7 divided by 0.1, which gives me 70. If I moved a little bit closer to 2, so 2.01, that gives me 7 divided by 0.01, which would give me 700. Right? As I get closer to 2 from the positive side, the numbers are approaching positive infinity. So this infinite limit would be positive infinity. So if you don't have a calculator available to you, whether you just don't have one next to you or whether you are not allowed to use one for that question, you can look and see what the signs of the numerator and denominator are going to be, right? And if one's negative, one's positive, well, it's going to be approaching negative infinity. If they're both positive or both negative, then that one-sided limit's going to be approaching positive infinity, right? I think I said negative infinity if one was negative, one was positive. At least I should have. So multiple different ways. You can use a graph, you can use a table, or you can take the analytical approach if you don't have access to your calculator. All right, let's see what is next. We're now going to need to talk about what goes on with the actual limit once we've determined what the infinite limits of the one-sided limits are. Before we do that, I just want to quickly look at part D. I know we're going a little out of order, but that's because we just discussed the answer to part D. So it says, when we identify that a discontinuity is a vertical asymptote, how can we figure out whether a one-sided limit is going to positive infinity or negative infinity? Think about the numerator and denominator. What do we need to look for? So we just talked about this, right? If the numerator and denominator have different signs, then the infinite limit's going to be negative infinity, right? If they have the same sign, then the limit's going to be positive infinity. So you just need to check the sign, pick a number close to whatever your x value is approaching on either side to see what the one-sided limits are going to. And you just have to check the sign. You don't have to find the specific number, especially if you don't have access to a calculator. You just need to figure out what the signs are. That being said, once we find out what our one-sided infinite limits are, we then need to make a judgment about what, sorry about that. Let's go back up here. We then need to make a judgment about what our actual limit is going to be. So I'm going to rewrite what our one-sided limit was here for A. Okay, so this one-sided limit was going to negative infinity, and this one-sided limit up here was going to positive infinity. And now we need to talk about the actual limit. This goes back to our very first discussion on limits. I think it was lesson 1. And if the two one-sided limits are the same number, so if both the one-sided limits were equal to 5, then the actual limit would be equal to 5. But if the two one-sided limits have different values, right, like 5 and 10, well, then we know that the limit doesn't exist. And this works the same way for infinite limits. If the two one-sided infinite limits are infinity and negative infinity, then the actual limit will not exist, right? Because the function's not approaching the same infinity. If they are both approaching positive infinity, then the actual limit does exist, and it would be whatever infinity both the one-sided limits are approaching. But based on our work right here, the actual limit, the infinite limit, would not exist because the two one-sided limits are approaching negative infinities. And you could spell that out in words if you need to go back and re-listen to what I just said. But it goes back to our initial understanding of the relationship between one-sided limits and the actual limit. We're actually going to stop here. We're almost at about 15 minutes. In the next video, we'll work through some practice problems as well as look at the calculus way to bring together infinite limits and vertical asymptotes. So hope to see you then. Until then, this is Mr. Fawcett, and have a great day.